Okay, I don't know if you can see my screen.
Yes, from my end, I can see.
Lovely. What about the others?
Doc, we can see.
Oh, good. Okay. Now, this is the address resume protocol. And let's see, the objective for this course is we're going to compare the rules of MAC address and the IP address. Analyze app by examining Ethernet frames. And then we're going to look at how app requests impact network and host performance, as well as potential security risk. And so looking at MAC address and the IP address, the MAC is just the media access control. You notice the two of them actually are domiciled in your system. At every point in time, you need those two for effective communication. So here, let's look at the destination on the same network. So the two primary addresses assigned to a device on an Ethernet LAN. What are they? The MAC and the IP address. And the description for your physical address, which is your MAC address, is used for Ethernet NIC, your NIC card, which is the NIC port you have in your system, NIC port. You also have the Ethernet port in switch and all that. If the destination IP address is on the same network, the destination MAC address will be that of the destination device. And so usually it will always look at the source IP address and then look at the destination IP address and map it together before any packet is being sent or frame is being sent across the network. But we're looking at that which exists within the same network. Remember, it has to have the same, they all belong to the same subnet mask. So the logical address, which is the IP address, is used to send packet from the original source to the final destination. The destination IP address may be on the same IP network as the source. And you should know that most applications use domain name, which is a DNS, to determine the IP address when giving a domain name such as www.cisco.com. So the DNS helps to actually resolve your IP address. And if that means at every point in time you're browsing and you're visiting any domain, always note that your DNS is needed. And our advice here at this point in time, it is good you have your DNS set up in your own network. Most folks use 8.8.8 as their DNS. It's not bad, but that tells you that your system has to go through that route before it gets back to your network. So that actually can add some latency or delay, as the case may be. So it's advisable that you have DNS actually set up within your organization, of which CentOS will do that for you, help you get, if you install CentOS on the server, you can actually activate the DNS with it. I've done that before and it works perfectly well. And so destination on remote network. When the destination IP address is on a remote network, there's network outside the main, maybe probably a private network or network outside the across your main network is referred to as a remote network. The destination MAC address will be the address of the host default gateway, as you can see from the diagram here. So the process in the figure is as follows. The router will examine the destination IP for address. Remember, you have a router here. So if you're sending anything from PCA through this router R1 and is going out of the network, it has to resolve the destination IP address first and be sure that it's captured on its IP table before such packet or frame is being forwarded. When the router receives the Ethernet frame, it de-encapsulates the layer 2 information. I remember when we talked about de-encapsulation, it has to remove the header. So using the destination IP address, the router determines the next hop device and then encapsulate the IP packet in a new data link frame for outgoing interface. Outgoing interface in the sense that it's going through the interface of your router, which of course transmit frames. So if the next hub device, remember I told us that when we say hub, we're referring to routers. So if the next hub device is the final destination, then the destination MAC address will be that of the device Ethernet NIC. And so this is how the communication flows work when it comes to a system sending an information or resources from one point to the other across a network of this nature, looking at it from the source to your destination. So let's quickly look at what app is, an overview. The figure to your right gives you a very clear information about the app. So the figure illustrates a problem when sending a packet to another host on the same local IPv4 network, because the IP address is known, but the MAC address of the destination definitely is not known in this case. So a device uses address resolution protocol, which is the app, to determine the destination MAC address, meaning that it does not know what the MAC address is. So you need to create an app. The app is more or less like sending an announcement and trying to capture where the destination address is. And so the MAC address of a local device, when it knows its IPv4 address, the app provides two basic functions, which you must always remember. One, it resolves the IP address to the MAC address. And two, it maintains a table of IPv4 to MAC address mappings. So that's the function of an app at every point in time. And you can actually check your app directly from your system. So the app functions, when a packet is sent to the data link layer, like you can see in this case, this is a switch. Remember, a switch is a broadcast domain. So the switch will always send information across through broadcast. So we're saying that it is encapsulated into an Ethernet frame. The device refers to a table called the app table, or what we call the app cache. Remember, when you restart the entire system, the whole table is cleared because it's a temporary memory to find the MAC address that is mapped to the IPv4 address. So if you recall, one of the functions of the app is that it will always map the source IP address to the destination MAC address. So in this case, you can see here that the first thing is that to check refers to this table called app table, or the app cache in its RAM memory, to find the MAC address that is mapped into the IPv4 address. So the sending device will search its map table. That's the first thing to do. To search its map app table for a destination IPv4 address, and then the corresponding MAC address. So if the packet destination IPv4 address is on the same network as a source IPv4 address, then it will send. So if the device locates the IPv4 address, its corresponding MAC address is used as a destination MAC address to the frame. And so this is actually the main function of the app. It helps you to resolve this before any packet is being sent or frame is being sent across the network. There's a video here you need to watch to see how the operation of the app actually is being carried out. So when a device needs to determine the MAC address mapped to IPv4 address, and no entry is found for the app IPv4 address in its app table, then an app request is sent. So recall that when it already sent this app, it's able to have an app table. The app table is that now it has resolved the source IP address to your destination MAC address, and that has been captured. But at any point in time, it checks and it's not there. It starts to make a request. A request has to be sent so that it can capture the destination MAC address, and so that the next time it's going to send to just forward. So if you click the video, this is not clickable here, but in your own account, once you log into the data card, you should be able to play this. And so the video app operations as the app reply, only device with the target IPv4 address associated with the app request will respond with an app reply. And that's basically the summary of app itself. So removing entries from an app table. For each device, an app catch timer actually removes the app entries that have not been used for a specified period of time. So you have a timer. In this case, this is an app, and the catch you're talking about is a temporary memory, of course. So it's like a way of it clearing up this table, because this memory you have is not unlimited. It can actually be choked with so much entries. So what we're saying here is that after a specified period of time, it has to clear what you have there. So the times differ depending on the operating system of the device. Commands may also be used to manually remove some or all of the entries in the app table. Remember, this also takes part of your memory, system memory, even the network memory and all that. So after an entry has been removed, the process for sending an app request and receiving an app reply must occur again to enter the map in the IP in the app table. So the meaning that even when it's clear, and then there's going to be a new communication between two systems, this whole process has to be reinitiated all over, meaning that an app request will be sent by the source device, and until that whole process is completed again. And then it builds a new app table. So on the Cisco router, how do you check this out? You say show IP app command is used to display the app table. And once you issue this command under the router, remember this, you're doing it at a protocol, the privilege exec mode here. So you can see show IP app, and then to display the protocol, to tell you the, you can see the IP address, you can see the hardware address, and then you can see the interfaces where this is happening. So the dash key actually gives you the app table. So on the Windows 10 PC, the app-a, which you can see here, command is used to display the app table on the PC. So this is for a router and this is for a PC. So right here, right where you are right now, you can just try it out and see on your PC. Of course, you've been on the internet browsing. So it means that your system has actually initiated a lot of app requests. And so one of the ways to validate or test this is to actually initiate those commands. So I advise everyone right now to just try it on your system and see if it will display. Some of you, your own might be more than this. You might have so many. So of course, some with dynamic, some with static, as the case may be here. And then, like we said, after a period, it is cleared, and then the whole process is reinitiated again. The reason why we're doing this, we're actually teaching you this right now about the app, is because the hackers also take advantage of this app. It becomes a problem in as much as the system, the router, they all use app to learn about the destination MAC address and resolve the source IP with the destination MAC address. And that actually helps communication to be very effective and very consistent. However, because of the nature of the app, the man in the middle, you know, somebody who wants to hack can come in between. And when a system is initiating an app, you know, the guy can just, you know, falsify it as if he's the destination system and then provide the MAC address. And then the source system will just send the legit information and the guy in the middle will just capture it. So this is also a challenge, and that's the reason why you need to learn this and do it more. So there's a Wireshark actually in your CyberOps station, and in this lab you do the following: you capture and view Ethernet frame in order to investigate app and the IP and MAC address, and then capture and analyze ICMP frames. The procedure for this scenario is actually in the lab. Once you just follow it sequentially, you'll be able to do that. So let's look at the issues. Like I said, there's an issue with that app broadcast. So as a broadcast frame, an app request is received and processed by every device on the local network. So on a typical business network, this broadcast will have been minimal impact on network performance, of course. But if many devices start accessing network services at the same time, there can be reduction in performance, because when all the systems are actually initiating app requests, trust me, you're going to have a depletion, or you have a high utilization of your memory. And of course, that will actually degrade the performance of the network or reduce the performance of the network. So if a device sends out the initial app broadcast and have learned the necessary MAC addresses, any impact on the network will be actually minimized. So there's app issues, app broadcast and app spoofing. So what's the app spoofing? So the use of app can lead to a potential security risk, like I said earlier, in some cases. So a threat actor uses what we call the app spoofing to perform an app poisoning attack. And it is a technique used by threat actor to reply to an app request, you can see, for an IPv4 address belonging to another device, such as the default gateway. So the threat actor send an app, you can see here, reply with his own MAC address, because recall that there's already a request, so he has to reply with his own MAC address. The receiver of the app reply will add the wrong MAC address, which is that of the threat actors. You can see it in the picture here, and then send this packet to the threat actor. So he does not know that because it's already added in the app table. What does he do? It just forward the legit packet or frame to the threat actor. So there's a video you need to watch to see how that plays out. So this is a summary of what we've looked at so far. App is good. App helped for communications, aid communications. An app, if being carried out with so many systems on the network, as the number of systems connected to the network increases, the app also increases, and that actually there's a reduction in performance of the network. And then we said that this same app can also be interfered by threat actors or by hackers by actually responding with a falsified MAC address, thereby allowing the network to place its MAC address on the app table, and then they'll be able to have access to legit information. So that's for module 8. Is there any question? If there's any question, I would like to respond to that, or else we can move ahead. Is there any question? Okay. So if there are any question, then we'll just go straight away to the next module, which is module 9. Okay. And module 9 actually is the transport layer. If you recall, the transport layer actually is the layer 4 of the OSI model, and it maintains end-to-end data integrity. So if you look at the OSI model, which is a standard, which is more or less like a reference model when it comes to communication, you all agree with me that from the application, the presentation, the section, the transport, the network, and then your data link layer, and then you talk about your physical. So looking at the transport layer the way it is, you all agree with me that the transport layer plays a very vital role. It maintains end-to-end data integrity. It ensures that once there's a problem, it triggers it, it helps. Sometimes it has to trigger layer 2 to perform FRC through the CRC, which is a cyclic redundance check, to compute what is coming in with what is at destination. If it does not, if it's not in conformity with what was sent, it will discard it. So the transport layer plays a very strong role when it comes to communication. So let's quickly look at the objective here. We actually going to look at how transport layer protocol supports network communication. And then we look at how the transport layer establishes communication section, and then how the transport layer establishes reliable communication. Very important. So let's look at the characteristics of the transport layer. The transport layer is actually responsible for logical communication between your applications running on the different hosts. So you agree with me that the transport layer actually provide different ports, or do I say the different access for effective communication. The transport layer has no knowledge of the destination host, of course. The type of media for which the data must travel, it does not want to know about that, but the path taken by the data. So the congestion on the link or the size of the network does not is not an issue when it comes to the transport layer. The transport layer actually has two main ways of sending out its data. It's either through TCP, which is the transmission control protocol, as you can see there, the last item down here, and also through the UDP, which is the user datagram protocol. So for the TCP, it is connection, and then from the UDP, it is actually connectionless. So you expect some level of acknowledgement when you're using TCP. When you're using UDP under a transport layer, it does not. So we are saying that one is reliable, which is the TCP, and the UDP is actually unreliable. When we say unreliable, that does not mean it is not important. It is. Your voice, your video on the network is being sent through the UDP, which is a user datagram protocol. So you can see a demonstration using the TCP IP and then showing the relationship where the transport layer interacts with the other network. So you can see that union. So the transport layer has many responsibilities. Each set of data flowing between a source application and a destination application is known as a conversation and is tracked actually separately. And like I said, it goes through different ports and sockets. So it is the responsibility of the transport layer to maintain and track these multiple conversations at any time. As shown in the figure, a host may have multiple applications that are communicating across the network simultaneously at the same time. All these are made possible because all these can run separately and new ports can be opened for them. So most networks have a limitation on the amount of data that can be included in a single packet. So data must be divided into manageable pieces when it's being transmitted. So let's look at it, the segmenting data and reassembling segment. Remember encapsulation, the process in which your data is broken down. We say this is segment, but the way the transport layer works is that at the end of the day, when it gets to the destination device, everything has to be reassembled. Because it's one thing that your data has been interleaved, meaning that it has been broken down into smaller forms. It's another thing that this data that has been broken down should be able to reassemble and give you your final output. So it is the transport layer responsibility to divide the application and then into appropriate size blocks and then reassemble them. It also, depending on the transport layer protocol used, the transport layer actually blocks and are called either segment or datagram. So the figure actually shows the transport layer using different blocks for each conversation. The transport layer divides the data into smaller blocks, segments or datagrams, and that are actually easier to manage and being transported across the network. So here we look at the transport layer responsibility in terms of add header information. The transport layer protocol also add header in information containing binary data organized in several fields to each block of data. Remember, this will happen when it's going down through probably to layer 3. So the header information is used by the receiving host to reassemble the blocks of data into a complete data stream for the receiving application layer program. So it's going across to the application layer if you're looking at the TCP IP, or it is going down to your network, of course, which it will actually be today that becomes the packet in this case. So identifying the application. The transport layer must be able to separate and manage multiple communication with different transport requirement needs. Like you can see, this is 110. We have port different applications. So this is like to show you the different services are run. When it's 110 is the POP3. And then it is 80, that's port 80 for your HTTP. And then you also have port 531. That's for the internet chat. And then we also have port 25, we have port 23, we have port 22, port 21. These are well-known port numbers. They're actually used for different applications and services. So as shown in the figure, each software process that needs to access the network is assigned a port number unique to the host. So conversation multiplexing, sending some type of data across a network as one complete communication stream can consume all the available bandwidth, which is very correct. So if you're going to send everything in one form, but we're saying that that is the role of the transport layer. The transport layer comes in and make sure that whole bulk of information is actually broken down into segments. So the transport layer protocol, so IP is consigned only with the structure. As a transport layer, you can see the IP is also consigned with structure. If you look at it in the internet layer, that's in the TCP IP. Of course, in your OSI model, is a network layer. So the IP does not specify how the delivery or transport of the packet takes place. Remember, it is media independent, and it does not guarantee delivery. So the transport layer protocol, the TCP UDP, specify how to transfer messages between hosts and are responsible for managing reliable requirement of a conversation. The transport layer includes your TCP and your UDP protocols. The different applications have different transport reliability requirements. Therefore, TCP IP provides two transport layer protocols as shown in the figure. And those are the TCP and the UDP. The transmission control protocol, which is the TCP, like we said earlier, it's one part of the transport layer, and it's actually reliable. It's full feature transport layer protocol. It ensures that all the data arrive at the destination. So it guarantees you delivery. It's the only layer that has its connection across all the other layers. So the transport layer at every point in time plays active role across the entire layer of either the OSI or the TCP IP. The TCP provides reliability and flow control using these basic operations. Number and track down data segment, acknowledge received data. It also do what we call retransmit any acknowledged data after a certain amount of time. It does what we call sequence data that might arrive in wrong order. And then it also sends data at an efficient rate that is acceptable by the receiver. As you can see here, the transmission control protocol is the TCP. In order to maintain the state of a conversation and track the information, the TCP must first establish a connection between the sender and the receiver. That means this must be established first. To know too well that the TCP, like we said, has a connection between the source and destination. That means at every point in time, with the help of a TCP, it must be able to ensure that there's an established connection between the two end systems. So this is the TCP header, as you can see, with the sources for an IPv4 and the destination, which is 16. So if you put that together, you get 32, as you can see also. So in this case, to track the state of a section, the TCP records which information has sent and which information has been actually acknowledged. Remember, on the TCP, it acknowledges, it also does record sequencing, it does flow control, there are a number of attributes, and that's what we actually looked at as some of the characteristics of the transport layer. And still on the header of the transport layer, it has a source port, a 16-bit field that is used to identify the source application. It has a destination port. That's what we call a sequence number. In this case, the 2-bit field used for data reassemble. It also acknowledgement number, header length, reserved control bit, window size to see if it can take more as you keep sending. And that is why on that window, you can see where is the receiver can say, oh, I can receive so number of bytes based on so number of time. If it's transmitting at so to a particular X amount of time, then it will receive at that level. So if you look at it critically, that is what windowing does. Then the checksum is 16-bit used for error checking of the segment header. And then urgent is a 16-bit field used to indicate if the contained data is urgent or not. So you can actually see this. It's just like a typical architecture of the transport header. Now, this is the user datagram protocol. It's a smaller transport layer protocol than TCP. It does not provide reliability. In other words, it is connectionless. The sender and the receiver UDP processes do not have to manage reliability and flow control. So this means UDP datagram can be processed faster than TCP. Remember, TCP will have to do acknowledgement and all that and wait. If there are no acknowledgement, it will also initiate the request all over again. Because the guy is designed to always acknowledge. So if there's a problem, an issue, it always trigger the layer 2 to resend that particular information all over again. And so the UDP is also known as stateless protocol because it does not track information sent or received between the client and the server. So this is actually a very good insight of what the UDP is. It divides that into datagrams that are also referred to as segments. So it helps also to break down this and then reassemble them. Still on the UDP, and then this is the header of the UDP. It has, unlike that of the TCP here, it has the source port 16, destination 16, and there's a length and the application layer data size. As you can see, it actually varies, but you can see here you just have the source port and the length, and that's all. And that's for the UDP. So let's look at the socket pairs. The source and destination port are placed within the segment. So the segment are then encapsulated within an IP packet. The IP packet actually contains the IP address of the source. Remember, the IP packet will always contain both information at any time you want to send. So if you look at a typical IP header, you will have seen that there's a source and a destination. So the socket enables multiple processes running on the client to distinguish themselves from each other, and multiple connections to a server process actually to be distinguished from each other. So the source port number acts as a return address for the requesting application. The transport layer keeps track of the ports and the application that is initiated the request so that when a response is returned, it can be forwarded to the correct application. So you see, it has to keep a track of this port. Okay. Hello, can we hear me? And still, hello?
Yes, we can hear you.
Oh, thank you very much. Still on the transport layer, looking at the socket pairs. In the figure, as you can see here, this is the well-known port numbers as port 21. And you can see to open new socket, it all depends on the number of corresponding windows or probably applications or different segment of application that is being opened. So in the figure, the PC is simultaneously requesting FTP, which is a file transfer protocol, and web services from the destination server. So the FTP request generated by the PC includes the layer 2 MAC address and then the layer 3 IP address. Remember, that's what the request would be for destination. So the request also identify the source port number and then the destination port, identifying the FTP services on port 21, as you can see here. So the host also has requested a web page from the server using the same layer 2 and layer 3 addresses. Remember, when we talk about the layer 2, layer 3 addresses, we're still referring to your MAC address and your IP address at any point in time. And still same, it is using the source port number, which is 1099. In this case, you see this is like a dynamically port numbers because this port will be generated as you keep clicking on new sections. A new socket pair will be opened. So you can see here is the IP address. This is a new dynamically port numbers being opened. To just give you a guide that as you keep opening new sections or new socket, you keep having this number. So we refer to them as dynamically port numbers. So the transport layer section actually, let's look at the description of a transport layer section. The TCP server process. So each application process running on a server is configured to use a port number. And the port number is either automatically assigned or configured manually by a system administrator. So an individual server cannot have two services assigned to the same port number within the same transport layer. No, one has to go for each. So a host running a web server application and a file transfer application cannot have both configured to use the same port number, such as TCP port 80. So one has to use it per time. So an active server application assigned to a specific port is also considered open. So which means that the transport layer accepts and processes segment and addresses to that port. Any incoming client request addressed to the correct socket is accepted and the data is processed in the same server application. Remember what we're saying in summary is that your system will always open new port numbers, especially for the different sections. Like in this case, the TCP port 80 is for your HTTP. So that means that is the services that you keep providing as long as it comes to port 80. So there can be many ports open simultaneously on the server, one of each active server application. So each of those ports, even when you have them, was actually built for a particular application of services. So the TCP server processes, you can see here the client sending TCP request is actually requesting for a web service, and the client 2 is requesting email service of the same server. So if you look at it critically, both of them must be on the same network in this case. And then you can see the HTTP, which is port 80. You can see a NCTP, which is a simple net transfer protocol. And then you can see the source port here, in as much as you have a HTTP request being made, but you have a source port number. And then you have a destination port, which if you look at it critically, your destination port is port 80 in this case. So we can see that this system also has client 2 have initiate an SNT request, but then the source port number is 5112. So you can see that's different port numbers, and the destination port is actually port 25. So in this case, that is the NSMTP port number. So the response source port. So in this case, the source port in the server response is the original destination port in the initiated request. So like I said, it will always open new port numbers for the new sectional request as you go. But those numbers that are being generated are actually dynamically set by the network. So the TCP connection establishment. In TCP connection, the host client must first establish connection with the server. That's the first thing, using the three-way handshake. So it has to first of all establish a connection, and then the TCP connection establish the steps are what? One, it will synchronize. That's in the bid of trying to check on the other system. So synchronizing is a way of trying to have some level of establishing the connection. And then in 2, it has to acknowledge and synchronize. So the server acknowledges the client to server communication and request a server to client communication section. And then in 3, it has to acknowledge finally. So the initiating client or acknowledges the server client communication section. So you can see this will refer to as a 3-way handshake. So the section termination, let's see when this happened at the transport layer. So to close a connection, the finish, which is the fin control flag, must be set in the segment header. So to end each one-way TCP section, a 2-way handshake consisting a fin segment and an acknowledgement segment is used to actually terminate any section at every point in time. So therefore, to terminate a single conversation supported by TCP, 4 exchanges are needed to end both sections. Either the client or the server can initiate the termination. And remember, we said if that has to happen, there must be some 2-way handshake. And another way for the fin, so that means you're going to have both the fin and the acknowledgement at the same time. It's used for that purpose. So the time client and server actually use as a reference to for simplicity. But any 2 hosts that have an open section can initiate the termination process. So even as much as you keep saying client server, it's still all about communication across 2 devices. So when all segments have been acknowledged, the section is then finally closed or terminated, as the case may be. So the host track each data segment with the TCP and exchange information about the data is using the TCP header. TCP is a full duplex protocol, meaning that it always can send and receive at the same time. Quickly, let's look at the 3-way handshake. The function of a 3-way handshake. 1, it must establish the destination device is present on the network. So in the course of synchronization, it must establish that the destination system is available. It verifies the destination device has an active service and is accepting requests on the destination port number and initiating client intends to use. So it must always make sure it checks this to be sure that it has requested a destination port number and it has established. But if it is not established, then it will be difficult to actually send any information or send any of the data. So after the communication is completed, the section are closed and then the connection is actually terminated. So here is a typical this gives us a clear deep understanding of the TCP 3-way handshake analysis. So the 6 bits in the control bit field in the TCP segment header are also known as the flags. So what is a flag? A flag is a bit that is set to either on or off. That's what the flag is. So it could be. So the 6 control bit flags are as follows. We have the urgent, which is the pointer field significant, and then we have the acknowledge, the ACK, acknowledgement flag used in connection establishment and section, and then section definition, and then we have the PSH, which is the push function. We have the RST, which is a reset the connection. So this is actually an analysis of a 3-way handshake, and then we have the fin. Remember, we talked about the fin also being used as one of the process to stall or to terminate connection. So here is a video you need to watch. This video actually talks about the 3-way handshake. So you watch it, it gives you a more deeper understanding of the 3-way handshake. So transport layer reliability. How reliable is the transport layer? There may be times when either TCP segment do not arrive at their destination. It's possible, or arrive out of order. So what happens? For the original message to be understood by your recipient, all the data must be received and the data in this segment must be reassembled. We said that is one of the core mandate of the transport layer. It does not transmit the bulk information as it were. It's going to break it down into segment, and once it gets to the destination, it will reassemble it and give you your full data. And during section setup, an initial sequence number is set, which represents the starting value of the bytes that are transmitted to the receiving application. So the sequence number is for what will be sent as an identification so that the receiving device will know, okay, now I'm set to go, and now I can see what I've been asked to send them. So I'm going to respond with a particular size of byte, data byte, and then another, and then it will initiate another number again. And then this time around, the sequence number again is purification. So it helps to either say, okay, are you increasing the size of data, or are you actually reducing it? So this data byte tracking enables each segment to be uniquely identified and acknowledged. Missing segment can then be identified. So the ISN is effectively a random number which prevents certain types of malicious attack. So we can see the guaranteed order of the TCP. And still on the TCP, you can see here that the segment source number indicates how to reassemble and reorder received segment, as shown in the figure. So the received TCP process places the data from a segment into a receiving buffer. So segments are then placed in the proper sequence order. Remember, the reason why it's being arranged this way is so that once it gets to destination, it will reassemble them. So any segment that arrives with sequence numbers that are out of order, not in place, not in the official priority ways in which is exchanging between the source and the destination, we're saying that that field for that are out of order field are held for what later processing. That means it will reinitiate that whole process all over again. So when the segment with the missing byte arrives, this segment are processed in the order based on the arrangement. Remember, this is already broken down into segments, and as it travels through the network, it must get to destination, and that order that enables it for you to be able to get your information full, as the case may be. So the TCP reliability sequence numbers and acknowledgement. So you need to watch this video, play it, and see. It gives an insight, a more demonstration of how the sequence numbers and the acknowledgement works. And then data loss and retransmission. Remember, data can be lost and data can be retransmitted. So TCP provides methods of managing the segment losses by retransmitting the segment for unacknowledged data. So the sequence number and acknowledgement number are used together to confirm receipt of the byte of data contained in the transmitted segment. So the sequence number identifies the first byte of data in the segment being transmitted. And then the TCP uses the acknowledgement number sent back to the source to indicate that the next byte that the receiver expects to receive. So this is called exceptional acknowledgement. You see, at every point in time a sequence number is sent, there must be an acknowledgement number. All this is to give a signal back to the receiver that now you can now send. So just recall that if there's a delay, like we said earlier, if it's a delay for a period of time, the transport layer will still look at it and say, okay, fine, let this be retransmitted all over again. And so there's a time frame for it to do that. And that's the reason why you have these numbers. So these numbers are like tags, that helps an algorithm already built in. It helps the transport layer to be able to tell at every point in time whether there's some issue along the communication line or not. So prior to a later enhancement, TCP will only acknowledge the next byte that is expected. Okay. So the TCP flow control remember, we're looking at most of these things we're discussing are the attributes or the characteristics of the transport layer. So we've talked about the sequence number, we've talked about the acknowledgement numbers, we also talk about windowing. Here we're looking at the flow control or also the window size and acknowledgement. So the TCP also provide mechanism for flow control. Flow control is the amount of data that the destination can receive and process reliably. So flow control helps to maintain the reliability of the TCP transmission by actually adjusting the rate of data flow between source and destination. So to accomplish this, the TCP header includes a 16-bit called the window size. So to be able to establish that. So the window size that determines the number of bytes that can be sent before expecting an acknowledgement. So this is the way it works. Here, the flow controls just help the transmission to look at the rate of data that is flow from the source and the destination. And then it also helps it to be able to check out the amount of data that the destination device can actually process reliably so that it does not send more than what it can take. Sometimes if you look at it when it's sending it, you can see it's okay. If it's sending a so byte, this is the amount of time to take. And sometimes it will reduce. All that is because there's a check to see what the destination can take at a particular time frame. So the acknowledgement number is the number of the next expected byte that we've explained before now. And the window size is the number of bytes a destination device with TCP section can actually accept and process at one time. So we've explained the flow control in terms of the size of the byte of data that the destination can be able to take still on the flow. So but here, I just want to talk about the maximum segment size, which is the MSS. So in the figure, if you look at it, that is actually the size. That's for the flow control of what the destination can take. So you can see here that the source is transmitting 1460 bytes of data within each TCP segment. So this is the maximum segment size that the destination device can actually receive. So the MSS is the part of the option field in the TCP header that identifies the largest amount of data in bytes that a device can receive in a single TCP connection. So the MSS size does not include the TCP header. The MSS is included during the three-way handshake. And like we said, this is one I would say that the maximum size of this byte or this data should not be more than one. If you look at it, we said it should not exceed this number. And this number, which is 1460 byte, is the allowable MSS number. And that you can actually get when the sequencing is initiated from the beginning. So you can see it here at the middle, just telling you that, okay, that's the size of the data during transmission. For the TCP flow control maximum segment, which we talk about the MSS, a common MSS is 1460 bytes when using IPv4. But a host determines the value of the MSS field by subtracting the IP and TCP header from the Ethernet frame. So remember that actually is another size of its own. So it has to separate that, minus that from it, from the Ethernet frame transmission unit. So on the Internet interface, the default MTU, which is 1,500 bytes. So subtracting there's the IPv4 header of 20 from it, byte, and the TCP header of 20. The default MSS size becomes 140. So that actually tells you that the actual size of the data or the frame itself. So the header is seen here at this point to be 20, and the TCP header is also 20. So if you put the two together, that is actually 40. So you can see at this end here, you have the FCS, which is your frame check sequence, of course, which uses the CRC as we earlier said. So port scanning is usually part of a reconnaissance attack. which you need to explore using the Nmap. And there are varying parts of scanning methods that can be used. So we'll explore how to use the Nmap utility. And the Nmap is actually a powerful network utility that is used for network discovery and security auditing. So there's a lab we're going to do with this to actually demonstrate how you can check the reliability of the transport layer. So in summary, the transport layer is the link between the application layer and the lower layers. So in the OSI model, if you look at the upper and the lower layer, the transport layer includes your TCP and your UDP. The TCP is reliable, the UDP is not reliable. The TCP is connectioned, the UDP is connectionless. The TCP gives you some acknowledgement, flow control, windowing, but your UDP does not. The transport layer is responsible for tracking conversation, segmenting data, and reassembling segment, adding segment header information, identify applications, and conversation multiplexing. So the TCP is actually stateful and reliable. It acknowledges data, resend your lost data, that is when it is lost, triggered it again, and then delivers that data in sequence order. So the TCP used for email and the web. So UDP is stateless and fast. It has low overhead and does not require acknowledgement. So you agree with me that it does not require acknowledgement and does not resend lost data. So once it is lost, it is lost. Just like when you're talking to somebody on the phone and you, for any reason, there's a network breach, there's no way it's going to resend that again. Rather, it is lost, it is lost. So that's why sometimes you say, oh, please, what did you say? Can you repeat yourself? It's because whatever is lost. But in the case of the TCP, there's some level where it waits for a while. Once there's no acknowledgement number being sent back, it reinitiates the process and then resend that process all over again. So you can see that this goes on and on and on and on. So this is a very big difference between your UDP and your TCP. Okay. And so that's a summary for module 9, as the case may be. So I think our advice, we will listen to the video again, go through the lab and play around this. So I think it will be nice tomorrow we take some labs as part of what we've done so far and use the Wireshark to track some of these things as we've said. And if there are any questions you have in the course of your practicals, you can also ask so that we can just play around this whole platform. And I want to believe that one, you need to know the reason why we're looking at the transport layer is because of the vital role it plays in sending out information. And then when you'll be doing most of these practicals, you should be sensitive to those port numbers. Like when you're talking about your DNS, when you're talking about your FTP, you should just be, those port numbers should be well known, meaning that we have to take our time to understand the well port numbers, the services of the applications that runs through those port numbers, and then they'll be able to identify which of them is dynamic and which of them is private. You must also, these are some of the questions, so that when you're carrying an investigation, you can say, oh, this is port 443. You know, this is a secure a link. And then you see port 80, you say, no, this is not secure. In some cases, they'll show you, oh, this is encrypted because it's on port 443. This is not encrypted. So those are the investigations you carry out. So the knowledge of the transport layer at that point in time is going to test your ability to be able to identify the port numbers and the services that they run, and then be able to interpret them when you have a real case scenario. So all that we're going to see in the course of the lab as we move on. So is there any question? And there's no question, I'm going to pause at this point and then we move on with the next module. But please, tomorrow we'll just walk around some of these labs and just try to see how we can carry out this investigation on some of these services. But as I promise you, as we go on further, all this knowledge you are gathering right from the beginning with the operating system, with the network, the IP, the app, the transport layer, all of them, once we start getting to the last part of this course, you begin to put them into proper use. I mean, all this stuff will come under one whole problem or one particular lab, and you must detect them out. So the earlier, the better you get used to these terminologies, the better for us. And that's why some of the folks here who are actually having some challenges with networking, I put them on CCNA1 so that you can, work through that and see how that can help, because some of these topics are actually treated in IT Essentials and they're also treated in CCNA1. So more or less for those folks that have done CCNA before, this is coming as a repetition. But for some of us that are new, there's no cause for alarm. You can still follow through, watch the video over and over, and then take your time, go through the material online, take your time, take the assessment, and you'll be fine. I don't think you have issue with that because they're just investigation we're going to carry out. So any questions so far, if I go on? Are we there? I hope I've not lost us. Hello?
Yeah, hi.
Okay. So if there's no question, I'm going to ask you a question. What's the difference between a port and a socket? We've talked about port. We talk about socket. So who can just tell me quickly what he or she understand by, because I've mentioned port, I've mentioned socket. So is there any difference or they mean the same thing?
There is a difference.
Okay, please, can you just tell us?
A socket is an IP address plus a port added to it.
Okay. Is anybody that has something? You say a port has an IP address and what?
And an IP address plus a port attached to it. That is a socket.
Okay, that's a socket. Okay.
Yes.
Okay. Then what about the port?
So the port is, take for example, 80. This is an identifier of the protocol.
Identifier of the protocol.
So
okay, any other person? That's a good one, right? Is there any other person who can make any contribution here?
Dr. Don.
Or do we see them as the same thing? You not ask them. Oh, they mean the same thing?
You are at the 8th module, and
Okay, go ahead.
we have just finished the module 3. And we are not only students, we are professionals. We work and we have just the week to learn the module.
Sorry, I didn't get what you're saying. Hello? Have I lost
You
us?
understand?
Yeah, can you come again, please?
I say that it's very, very, very quickly. We have just the week to learn the module. And we are professional worker. We work every day and have just the week.
Okay, I thought you're trying to answer my question, but I can see you have a concern.
Please repeat. I don't understand.
Hello?
Yes, I can hear you.
Okay. Can I go to your question? You're
Yeah,
asking about the difference between the port and the socket.
exactly. Yeah.
More specifically, a number is used like some maybe a device or computer. Having a number, like we can use that. Like if you're trying to build like something or trying to set up a server like Apache, you use the local host. The port of the local host is mostly of 18, or you can just modify it to 88. It's kind of tunnel.
Okay.
Yeah, and the socket is most combined of the IP address and the port number. Just for to
Okay,
transfer.
that's for the port. That's for the port, right?
No, the first one is for the port. The second is
Okay.
of the IP address and the port just to transport them. But port is more specific for a number used by a program or a computer or service like web service.
Okay, like web services, all those ones can be under, are you saying socket?
No, port. SSL port or
That's port.
yes, port.
Okay, that's port. So I can see you're talking more of the port here. So what happened to the socket?
The socket is more the combination of the IP address and the port number.
Okay, so a socket is a combination of both the port, the IP address and the port number. Okay, so invariably what you're saying is that when you have the two existing together, automatically that is a socket. And that will run as a section, right? So you could have as many sockets opened because you have the IP address tied to the port number. But in the case of the port number, it actually represents your application process. It has to do with your port number itself and does not indicate protocol being used. So it's just a number to show what kind of services is running there. Okay, I think that's a good one in summary. So why I'm asking this, because your student, of course, will ask you all those questions when you begin to use some of these terms interchangeably. So there's a need for us to take our time to know the difference between the two. Okay, so any questions so far? So we'll just look at module 10. I'll introduce module 10 and then I'll stop halfway and allow us to look at the assessment for that chapter. So gradually we begin to move away from the fundamentals and then begin to get into the mainstream. Here is network services. If you can see my network if you can see my slide very well, please can you just indicate, can you just raise your hand if you can see what I've just shared? Oh, lovely, lovely, lovely. Oh, thank you so much. So let's quickly look at network services. Quickly, what are the services that you have on the network? So we just go straight to the main objective of this course. And here we're going to actually look at how DCP services enable network functionality, how DNS services enable network functionality, and NAT services enable network functionality. Remember when we say DCP, we're talking about dynamic host configuration protocol. There's an automatic way in which your system acquires an IP address for connectivity. And then the DNS services, this is a domain name server. Recall we said is actually used to resolve a domain name, meaning that you need a DNS server to be able to tell you, oh, what is the IP address of w.cisco.com. A domain name server will also tell you what the IP address of your organization website is all about. So if any domain name, you need a DNS. Without a DNS, no domain name can be resolved. And so we also look at how file transfer services enable network functionality, and then how email and services enable network functionality. And then we look at HTTP services, how it enable network functionality. So DHCP like I said, is Dynamic Host Configuration Protocol. For IPv4 service, it automates the assignment of IPv4 address and the subnet mask gateway and other IPv4 networking parameters. So you can see even for topology to your right, it gives you a clear view that first you must have all those information in place. And when you talk about dynamic, you also talk about static. So if it is not dynamical, then it has to be statical, statically or connected. So the network administrator manually enters an IP address information on the host. If it does that, that's through the static. So when a host connects to network, the DHCP server chooses an address from actually a range or pool. So the only way DHCP works is that you must create a pool of an IP address. That means you must have a network address, and then you will move to list. In some cases, you can exclude certain range of IP addresses. And the reason why you're excluding is because you want to use them for static servers, because not all the systems are meant to be on DHCP. You have certain applications that you want to access in real time. You don't want the situation whereby one day you wake up and there's no IP address, or probably the IP address has been leased, the lease period has expired, and then some other system is picking it up. So you need to exclude certain range of IP addresses for that purpose. And so the DHCP operation, DHCP operations include the DHCP discover, DHCP offer, and the DHCP request, or also called the DHCP acknowledge. So when DHCP configuration device connects to the network, the client broadcasts using what we call the DHCP discover. That's the means of which it discover it broadcast, and then the messages to identify any available DHCP server on the network. So a DHCP server actually replies with an offer. So recall that the only way it can actually broadcast once there's a connection to show that there's an availability of DHCP is through the discover, and then the server replies with an offer message which offers a lease to the client. And then the client sends a request, in this case, message to identify the explicit server and lease offer that the client is accepting. So if the IPv4 address requested by the client or offered by the server is still available, the server returns the DHCP acknowledgement message. So if the offer is no longer valid, then the selected server responds with a DHCP NAC message. And if the DHCP NAC message is returned, then the selection process begins again with a DHCP discover. So what we're saying here is that this is the manner in which a DHCP client and a DHCP server communicate, meaning that before your system connects to a server that offers these kind of services, the first thing it has to do is there must be a broadcast, and then it has to be discovered. And when it's discovered, the server will do an offer. And when the offer is done, then the client has to send a request, in this case, knowing fully well that there's availability that now I can be able to make a request, and I'm sure, and that request will be acknowledged. And once that request is acknowledged, we say that if the offer is no longer valid, then the selected server responds with a NAC message. And if the NAC message is returned, then the selected process begins again and again. So this is the way that the DHCP carry out its own operation. Each time there's a setup or connectivity between a client system or a client DHCP system and that of a DHCP server. So for a DHCP, we have the version 4, and then it's used for all DHCP transactions. We have a DHCP message that encapsulated the DHCP UDP. Remember the UDP, which is user diagram protocol. And then below is the field covered in the structure of the DHCP version 4, which in this case you can see the hardware type as a flag, the client hardware, the address length, the client IP address, and the server name. And then you can see the hops and the IP and the boot file name. So this is just the field structure of a typical DHCP message. So let's quickly look at the DNS. So we've seen the importance of the DSCP, and we said all those processes have to take place. And remember, when you have this process initiated, it means that there's a back and forth packet that is exchanged between the client and the server, which can also be vulnerable. So in this particular module, we're listing all those protocols in terms of their operations. And as I discussed this with us, we should also be looking at the vulnerability. Are there vulnerability in this DHCP? Are there vulnerability in DNS? That's what you should be looking out for, because that is the investigation you end up carrying out at the end of the day. So the question is that TCP is perfect, it's good because systems acquired IP dynamically, but there are procedure operations of the DCP that we have looked at. And these operations, are there ways that it can be hacked or threat actors can take advantage of them? Sure. So how does that happen? That now leads us to the labs to tell us how you can carry out the investigation. So the DNS is domain name server. Remember, we said we need that to be able to resolve our domain name. So the naming system provides domain name names and their associated IP addresses. So a DNS system consists of a global hierarchy of distributed servers that contain database name to an IP address. So it always map it and give you a typical feedback. So the client computer in the figure will send a request to the DNS server to get the IP address. And so that if it can address packet to that server. So in this case, the malicious DNS traffic can be detected through a protocol analysis and the inspection of DNS monitoring information. So the DNS domain hierarchy, you can see that here we have different types. We have the .org, we have the .au, and all that are found. All this hierarchy is just to tell you the categorization of the DNS system. And so we have a DNS lookup process. This actually helps to resolve the name to an IP address. The resolver will first check the local DNS cache. If the mapping is not found, a query will be issued to the DNS server. So you just check the cache first. The cache is more or less like a proxy DNS. So if the mapping is not found there, the DNS server will query other higher level DNS servers. So you can see the hierarchy here of which the way the DNS operates. So it checks from the server, it checks from the cache, it checks to the DNS server, and then it checks it based on the hierarchical distribution. So these are known as recursive queries. So this is the process in which it has to look up to see if there are higher DNS server that can help it. That means from your local DNS, you start to check which is like cache, and then you now have the main DNS, which is top at the hierarchical point. But it's good to have your own DNS. Like I said, it enhances the speed of your network. So steps involved in DNS resolution. First, the user types what we call the FQDN into a browser application address and field. Then a DNS query is sent to the designated DNS server for the client computer. And once that is sent, the DNS server matches the FQDN with its IP address. And the reason why it's doing this is because first, it wants to be sure that on the lookup, they're looking at the hierarchical stage of the way the DNS operates. It can actually resolve that name. So the DNS query response is sent back to the client with the IP address of the FQDN. And the reason why he's doing this is because, first, also note that because your DNS server is its job to resolve that domain name, because there's nothing like www.cisco.com on the network. So the network on its own cannot actually phantom what that is. So the only way it can do that is through the help of the DNS server. And that is how it helps to resolve this. So the role of the DNS is actually very, very important when it comes to communication. And of course, if that local process must take place, then you know fully well that there's some level of compromise can happen. And this is the reason why fully qualified domain name is used for that process. So the DNS query response is sent back, and then in this case, the fully qualified domain name will respond accordingly. So here we have step 5, which is the DNS server matches the FQDN with its IP address. Recall the FQDN is your fully qualified domain name. Okay, and then let's look at the DNS message format. This is the structure of a DNS message format. It uses UDP port 53. So recall here that your port 53 is your DNS. And then for DNS queries and responses, if the DNS responses exceed 512 bytes, that's the dynamic DNS is used. And the DNS protocol communication uses a single format called a message. The DNS uses the same message format for all type of client queries and server responses, error messages, and transfer of resource record information. So invariably, you should always note that in the course of your investigation, when you come across any display that tells you port 53, you know you're dealing with the DNS, because as you go on, those are some of the queries we'll be carrying out, and then you need to note this. So please always note down the vital information as you go on. And so the DNS message format, you can see the message section, question, answer, authority, and then description for each of them. This is just to give us the format of the DNS. And the domain, that's a dynamic domain name server system, allows a user or organization to register an IP address with a domain name as in a DNS. And then the subdomain is mapped to the IP address of the user's server or home router connection to the internet. So it helps to map up your system IP address or the IP address of the user server. So if, for instance, you have an existing server of the DNS, we're saying this is like having another way to get connected, you know, at the top level, the hierarchical level. So when a change is detected, the dynamic DNS, in this case, is immediately informed of the change and the mapping between user's subdomain and the internet IP address is immediately updated. So at every point in time, it checks to see if there's some changes from the user end. And if it is, then it will have to dynamically change it, because remember, your network comes under a domain. So if you change it, there's a need for that whole readjustment all over again. So it's better because this helps you not to reconfigure and keep reconfiguring the network each time there's a change. You start saying, okay, which DNS am I going to be on? So the dynamic domain name service provides service supplies the IP address to the resolver, second level DNS server. This DNS server, either at the organization or ISP, provide the DNS IP address to the resolver. So the WHOIS protocol is a TCP-based protocol that is used to identify the owners of the internet domain through the DNS. So the WHOIS application uses a query in the form of a fully qualified domain name, who is a starting point for identifying the potential dangerous internet location that may have been reached through the network. So if you open, let's say you have a new portal that you've actually set up. It's quite after a long period, you see this pop up in your mail, you know, the WHOIS domain and all that. Like we said here, it is a TCP-based protocol that is used to identify who is the right owners, you know, the owners of the domain through the DNS system. So there's a Wireshark you're going to use as a lab in this section to examine UDP and DNS capture. So to be able to differentiate between the UDP and the DNS. So in this lab, you complete the following objectives. You communicate with the DNS server by sending a DNS query using the UDP transport protocol. So use Wireshark to examine the DNS query and respond exchange with the same server. So I advise every one of us to play around this so that tomorrow we'll just look at most of these practicals we're talking about. So when I'm talking about UDP, you know what UDP is. We talk about DNS, you know what it is. So I advise to go through this whole material all over again and play around it. And then we have what we call the NAT. The NAT is the network address translation. It actually allows the device to be mapped up with a private IP address. So you can have you can have a static NAT. In other words, you can map one-to-one. You can have dynamic NAT. You can have a private, what we call a PAT, which is a port address translation, network translation. So you can actually have all these types of NATs, but in summary, what we're saying here is that when you have a private network and you want that private network to be announced on the internet or get connected to the net and to the public domain, the only way that will happen is through the NAT translation. So you can see that here at the middle, where you have an internet network and the internet network must go on a public domain. So you need a NAT to actually get that connection established. So NAT is used to conserve public IP addresses because you can have as many private IP addresses and just use one public IP address to announce them. And so it helps to conserve IP address. So what NAT works? In this example, PC1 with private IP address wants to communicate with an outside web server with a public address. So in this case, you see it is one-to-one, and then you can use a static NAT to map it in that case. So the port address translation, which I just said earlier, helps you to be able to map many to one. In other words, you can use many private IP addresses to just one. So when the device initiates a TCP section, it actually generates TCP or UDP source port value or specifically assigned queries. So in summary, the port address translation is a way to just help you translate as many private IP addresses you have through just a single public IP. Okay, so the file transfer and sharing services. We have the FTP, which is a file transfer protocol. We have a TFTP, which is a tribal file transfer protocol. So your FTP allows data transfers between a client and a server, which we know that before now. That's what FTP does. And then your tribal file transfer protocol is a simplified file transfer protocol that uses known UDP port number 629. We also use it also for your iOS on the Cisco router to actually upgrade. So if you're doing this, you can use that port number. So we need to note this down very importantly, of the function of the FTP and the TCP. And then we have a server message block, which is the SMB. It's a client-server file sharing protocol that describes the structure of a shared network. So the SMB is a client-server request response protocol. The servers can make their own resources available to clients on the network. Okay, so we have a Wireshark that will help us examine TCP UDP, so you need to note that down. And then email protocols. So email is stored and forward method of sending and storing, retrieving electronic message across the network that we know already. So email client communicates with the mail servers to send and receive email. So let's look at this in this case. So the email report has three separate protocols for these purposes, which is a simple mail transfer protocol, SMTP on port 35, which is for sending, and then the post office, which is for delivery, which is on port 110, and then we have the IMAP. So this helps in the email protocol. So anytime you talk about the email protocol on a network, SMTP, POP, IMAP come into play. So a client receives email using one of the two application layer protocols, either through the POP, which is like a delivery agent, or the IMAP. So the SMTP message format required message header and a message body. And recall, like I said, it's on port 25 that we can see. When a client sends an email, the client SMT process connects with the server SMT process on a well-known port 25. So when the server receives the message, it either places the message in a local account, if the client, if the recipient is local, or forward the message to another mail server for delivery in case it's outside that domain. So periodically, the server checks the queue for messages and attempts to send them again if the message is still not delivered after a predetermined expiration time. It is returned to the sender as on delivery. So you can see here that it has to wait for a critical period to check and look at the queue messages to be sure that this can be sent, and if it's not, it has to return back again. And that's why you have the delivery agent, and then you have the receiving agent, and you can see the mode of connection between the two. And the POP is used as an application to retrieve a mail from a mail server, port 110, and then the IMAP is the protocol that describes a method to retrieve email messages. So quickly, let's look at the HTTP. In case investigation is carried out, what does the HTTP is? It's the hypertext transfer protocol and markup language. So when a web address or a uniform resource locator is typed into a web browser, the web browser establishes a connection with the web services that is used, the HTTP. So let's take a look on a web page. It's open on a browser, example, http://cisco.com index.html. The browser actually interprets the three parts of the URL, which is what you can see here, the server name. It checks the protocol or the scheme, which is the HTTP, and then the index.html, which is a specific file name that is being requested. So it has to check that as step 1. And step 2, the client initiates an HTTP request to the server by sending what we call a GET request to the server and asks for the index.html file. And that is actually being embedded. That is where you have the IP address oftentimes. So the SMTP, the step 3 is the response to the request. The server send the HTML code for this web page to the browser. And the browser actually specify the HTML code and format the page for the browser window. So you can see the HTTP URL can specify the port on the server that shows that actually handle the HTTP methods. It can specify a query string and fragment. And like I said in summary, that the HTTP is not actually secure. So if you actually type stuff probably on that platform, it's actually plain. There are labs who do, you see the investigation and you see where it is plain. You can also report at that point in time that this is not secure, and then you also look at the HTTPS. All that is the reason why all this is being mentioned here. So the HTTP operation is request response protocol that uses TCP port 80. It is flexible but not a secure protocol. That's what I want us to note here. Okay, and then when a client sends a request to a web server, it will use one of the 6 methods specified in the HTTP. So the HTTP status codes are numeric, with the first number in the code indicating the type of message. The 5 status code groups are 1xx informational, 2xx when it's success, 3xx redirection, and then the 4xx. This is just to give us the status of the HTTP code, as it were. And what each of these means actually is to give us one, that the client should continue with the request, whether it's to continue the request, whether the request is completed successfully, whether the request has been accepted. So it's just the behavior of the HTTP itself. So this is the status of the code of the HTTP itself as when it's carrying out its full operations. Okay, so this is HTTP2. The purpose of the HTTP is to improve, the purpose of the HTTP2 is to improve on HTTP performance by addressing latency issues that existed in the HTTP version 1.1 of the protocol. So the HTTP2 actually uses the same header format as that of 1, but in this case, even though it uses the same header as that of 1, but it provides an improved performance than that of 1. Few important features of HTTP that a cybersecurity analyst must be aware of is 1, the multiplexing, the server push, binary protocol, and the header compression. These are essentially the 4 features that you must remember. So securing HTTP is the HTTPS. And like we said, the HTTPS is on port 443. So we're going to look at Wireshark to examine HTTP and HTTPS. You capture the traffic for HTTP, and then you also capture the traffic for HTTPS. I want everybody to do that investigation too and see what you get. And this is a summary of what the network services are on. So those services we look at the DHCP, we looked at the DNS, we also looked at NAT, as the case may be, and then we came back here to begin to look at the HTTP. So if you walk through this, you see we talk about the email. So they are all services, the services that run on your network. And going through this means that when you now want to carry out investigation, you're still also walking through those services on the network. So I want us to recall this, go through it over and over, and read through the material again, and then take the assessment before going to the lab. It will give you a deeper insight into what we're saying here. So at this point, is there any questions? So I can pause and round off for today so that we can meet tomorrow. Like I said, some of this investigation, we could just play around them tomorrow. It's going to be interactive because a number of you have actually done some of these labs and sent to me. So we're going to be discussing it out and then can move on from there. So any questions so far? Hello, are we there? So the section is recorded as usual. So I will just make it available. So,
Okay. Hello, Doctor.
Yeah, go ahead, please.
Okay, as I understand, we have a labs we have to do tomorrow to send it to you tomorrow.
Yeah.
Yes. I see when you when you're showing the slides, the labs about the Wireshark. Can we add the Wireshark in virtual machine?
Yes, there's Wireshark in the virtual machine. In your CyberOps station. Yeah.
In workstation, I can do that?
Yes. In the CyberOps station, there's the Wireshark.
Okay.
Yes.
I have some labs I don't understand how do answering the questions so that I don't send them to you. If I read more or understand how I answer the questions, can I send it again to you?
Yeah, that'll be perfect. Send it to me. I would put that up tomorrow and discuss with the team so you can have a better understanding. So those labs you're having, concern about, just send them to me. I'll discuss them tomorrow before we continue.
Okay. Thank you, Doctor.
That'll be fine. So please, if you have labs that you have some concern, you can just send them. I will bring them up again tomorrow and then we'll just review them together, just to explain it further. Bulus, I can see you have questions. Go ahead.
I am sorry, Doctor, but I am not have enough time because I am very loaded in my work. So I will concentrate on or focus on the labs for this 2 days for today and yesterday labs, but the labs what I didn't do, maybe I send it again in another time.
No, if you can send the labs you have not done and you have consigned, like I said, just send it to me. I will discuss them. I will discuss them tomorrow, talk about it, and then record it. If you're not available, the recording will be made available. You can just play the recording and just look at how we discussed it, and then you can update the record.
You're speaking too much fast for me.
Okay,
Not
okay, sorry.
catching all what you're saying. Even when you
Okay,
explain
so
something and not surely understand what you say.
okay, so if I really get you clearly, you said you have some labs that actually giving you some consign. Am I correct?
You meaning consigned?
You just
I
okay, what I
have
mean by consigned, you have some labs that are difficult that you think you cannot.
yes, yes.
Good. So those difficult labs that you think you cannot be able to carry out or to work on, you can send me those labs. Is that okay?
Okay.
Yes, send me those labs. If you have a problem with probably a particular lab, just tell me the particular lab number. Send it to me. I am going to work on the lab myself. I'm going to discuss it in the group online in the class tomorrow. I'll discuss it in the class. So if you are available, you'll be part of it. And if you're not available, it will be recorded. And then you have the recording.
Okay. Okay.
I don't know if this is clear to you.
I think I understand. Thank you.
Okay, so I'll be expecting you to send it to me. Is that okay?
Okay.
So are you going to send it right away? Do you have a lab
so,
number? Okay, if you can tell me the lab numbers, I can just write it down.
yes,
So
it's the wait a minute. It's 116. I don't understanding how it's I do.
1.1.6.
Yes, I don't understanding how I answer the questions. Even I understand the whole things, but the questions I don't know how can I answer them.
Okay, that is
Even
lab 1.1.6. Am I correct?
yes, and 2 and 1.2.3. This is and 1.3.4.
Okay. 1.1.6, 1.1.3, and 1.1.4. Am I correct?
Yes.
So we're looking at 0.3, 0.4, 1.6.
And the five the both of labs in five in chapter 5, both of them the first one I understand it how do I, but I don't see any question or have to answer them. It's 515.
Okay, is this 5.5?
Yes, I understanding how do the labs, but the lab, but I don't see any questions or what can I answering.
Yes, if you have a lab that does not require you to answer anything,
Yes.
just state it there that you have read the lab and you understood the lab and you're okay. I'll be fine with that.
Okay. But the 537 I didn't can do that.
Okay, that is 5 point what?
537 .3.7.
Okay, 5.3.7.
Yes.
Okay, fine. So I'll be discussing that tomorrow.
Okay, thank you, Doctor.
You're welcome.
Thank you very much.
Okay, so any other questions? I can see Fal, and then I can see Bulus. If you have any questions, you can ask now. Okay, there are no questions, then we're going to end the section for today. Then we meet tomorrow. So we'll be discussing some of the questions or challenges she's having. We'll look at it. And if you have anyone, you can also send the same, so we can look at it together. And that's the reason why we're instructors. We can interact and dissecate some of these issues. Okay.
Hello, doctor.
Yes, go ahead, please.
I have a question. What's the deadline? The deadline to the lab, the lab.
Sorry, you mean the labs, the number of labs you meant to do, or what?
Excuse me, he meaning the deadline for sending the labs to you, as I understand.
Yes, we said the deadline is actually Friday.
Friday for the chapter 5 to 1 to 5.
Yes, 1 to 5 this Friday, 1 to 5. One to 5 submit. You have to submit 1 to 5 Friday latest. Is that okay? Is that okay?
It's okay.
I said, can you submit your labs? I extended the date. I said you can submit your lab from 1 to 5 this Friday. But if you have it already, some of you have already submitted, so you don't have a problem. Okay, so catch you guys on tomorrow. We'll look at it tomorrow, and then remember to work on your labs. And if you have challenges, you can send that. So see you guys tomorrow. Good night from here, everyone.
Thank you, Doctor.
Yeah.
Good night, sir.